Good morning and welcome, everyone. My name is Jonathan Rowe. I'm here representing Autodesk Sustainability Solutions, and today you're here to learn about lifecycle assessment at the speed of design. Really quickly, the learning objectives for today, we're going to be understanding the fundamental LCA concepts for those of you who may be unfamiliar. Get some tips and tricks on how to efficiently conduct lifecycle assessments with some new software that you'll be learning about. Defining the appropriate scope for this sort of study, and learning how this sort of thing applies to the new credits within the LEED v4 rating system for lifecycle assessment of materials under the Materials and Resources credit category. Just a quick overview of our agenda. I'll be taking care of talking about the concept of at the speed of design analysis, and then we're going to be talking about basic concepts of LCA, understanding when it's appropriate to use lifecycle assessment, understanding how environmental product declarations, or EPDs, fit in with this, and again, relating to how this concept is relevant to the LEED v4 rating system and how Tally applies to these new credits. So, at the risk of being too basic, for those of you who are probably familiar with the concept of BIM, or Building Information Modeling, building information modeling is a process by which teams collaborate to build up a 3D virtual model of information-rich elements that describe the building, and it's commonly been associated with efficiencies of team collaboration, meeting schedule, scope, budget targets, and really this building information model can be the basis for a lot of different analyses, many of which are related to sustainable design. And at Autodesk, one of our visions is for these building information models to be the basis for conducting high-quality energy analyses early and often throughout the design process to lead to better buildings for the built environment. And the building information modeling process covers a wide range of activities, from planning to design to building and managing. But very importantly is the idea of building information modeling being applicable during the design phase and giving designers, planners, engineers, builders insight into how they can create better buildings, and this concept of information at the speed of design, rather than doing analyses that take days or weeks to get feedback on the performance of a particular concept, having that information available very quickly and very rapidly during the design phase to inform better decision making. So this could deal with basic site orientation, the infrastructure services that serve a building or a cluster of buildings, the transportation systems that serve that system as well, all the way through to actually building the building and managing it over time. And really this comes down to a concept where building information modeling, simulation services, and cloud technology create a virtual environment for designers and builders that is frictionless, flexible, and collaborative amongst the party stakeholders. And within Autodesk, our energy analysis capabilities seek to provide a lot of different simulation services that provide guidance for practitioners to get better insight into their design decisions. And a lot of this relies on cloud computing. Rather than having souped up computers that require a lot of computing power to do these sorts of visualization or simulation services, leveraging cloud technology to enable this to go faster, more rapidly, and give better insight for good decision making. So that's just sort of the overview of the concept of at the speed of design. I'm going to hand it over to the real stars of this presentation, Roderick Bates and Ryan Welch from KieranTimberlake, who are behind the development of Tally for lifecycle assessment with Revit. I'm going to turn that over to Roderick Bates.
Well, congratulations, everyone. You probably heard Star and Roderick Bates for the first and only time ever in a public setting. So with that, though, we'll slow things back down from the speed of design and get into life cycle assessment and really what that means as a concept. Some of you may know, some of you may not know, but fortunately I'll do something that splits the middle, because I'll give you a very abbreviated version. So life cycle assessment at its simplest form is this concept that with to the degree that we're referring to it is that the materials in particular of a project have an embodied environmental impact. For some of you that may sound simple, but in fact it's very unlikely when you as an architect are specifying your given materials, you realize that that cubic yard or a kilogram of concrete or what have you has with it a litany of environmental impacts associated with it from the point of manufacture, material extraction, all the way through to end of life. So, fortunately, there's some very smart people out there who are probably real stars in their own right, who have developed a methodology that is codified with the ISO regulations for accounting for these particular impacts. And ISO 14040 is really one of the primary means by which that is accomplished. So I'll take you quickly through what some of those steps look like. And really, this is sort of the overall process of life cycle assessment. And you can see it's actually one that's incredibly complicated and in some ways not necessarily compatible with the speed of design ethos that Jonathan was putting forward. But fortunately, we have a solution. So the first thing one needs to do when they're conducting a life cycle assessment is really understand why they're bothering to do this. Are they doing this just to learn how good or bad they were? Are they doing something perhaps to lower their overall impact, maybe compare two options to inform decision making? But that's really about establishing a goal. What are you trying to achieve? Or maybe you're just trying to achieve the LEED V4 credit. That's a fantastic goal. But the second thing you need to do is establish your scope of assessment. What exactly are you trying to study? And the key thing in the context of applying life cycle assessment to architectural practice is determining your functional unit. And your functional unit is essentially your unit of comparison or unit of assessment. And what your functional unit has to be is something that, if you say you're comparing two options, these things actually perform the same function over the same time period. So let's say it's a certain amount of insulation that's rated at an R value of 5, and it's supposed to last 30 years or something like that. That's your functional unit. So no matter if you end up varying your materials, things like that, the shape, dimension, what have you, it has to achieve that particular objective, that functional purpose. So let's say once you've done that, and you've done that over the scope of your entire building, you figured out basically, you want your scope of assessment might be a whole building assessment, say, and you realize there's a number of materials that have different lives in them, and each one of them will have sort of its discrete functional unit. The key then is you have to figure out how much stuff you have in the entirety of your building. So you really have to answer the Bucky Fuller question of how much does your building weigh? And the second thing, of course, with that is you have to know what is the impact associated with the manufacturing, maintenance, useful life, and disposal of all those things that you just went out and weighed. Fortunately for us, once again, that's a process that, despite being incredibly complicated, and this is an example of all those impacts associated with just, say, an aluminum extrusion, but this has to be repeated over for every single material in your entire building, and we're talking about thousands and thousands of materials. And this is something that no architect can be expected to do. So fortunately, there's very smart people out there whose entire business model is predicated upon providing this type of information. So you take this information provided by those particular database providers, and you combine that with a list or a bill of materials for the entirety of your particular project. So something like this might be just a very small section, but in fact, you would have an Excel spreadsheet that would go on for pages and pages if you actually had to quantify the exact kilograms and mass of everything that you have in your building. It's just an incredibly daunting task. So once you've combined these two things, basically all these impacts and processes with the amount of junk that you have in your building, you put these two together, you're basically going to get now the total amount of impacts. Maybe you'll get like the amount of sulfur dioxide emitted or the amount of methane released or things like that. But those sort of things really don't mean much to us. I mean, how do you say, sulfur dioxide is good or bad? What you really care about is these impacts and how they actually hurt the environment or they hurt people. I mean, that's really what we're trying to do. So there's mechanisms in place to take all of these raw quantities of various toxins and things like that and convert them into impacts that we can recognize. And those methodologies are basically called a categorization scheme. And one of the primary ones that's used in the United States is developed by the Environmental Protection Agency, and it's called TRACY. And TRACY puts these impacts into very distinct categories. And these are the ones that you'll find in accordance to the LEED V4 requirements. And I'll go through these in some detail. So the first one is global warming potential. And there's a lot of different gases that can accumulate to cause basically a global warming potential. It's not just carbon. There's a lot of other things like methane that have a similar impact. So what this does is it allows you to have a mechanism by which all of these various gases can be aggregated and then put into one sort of common term that has a direct environmental implication. The other one is acidification potential. In the process of manufacturing an enormous amount of good, just about any good you can think of, the industrial processes as well as the end-of-life scenario, maybe the harvesting of those raw materials, will cause a certain amount of release of pollutants into the atmosphere that will cause acidification. This will mean primarily the lowering of pH both in rain and water bodies. This can have certainly an effect on various ecosystems, crop damage, deforestation, things like that. And then, of course, from the perspective of an architect, if you're concerned about some of those beautiful older buildings that may have been built out of stone, things like that, this is an impact to that as well and cause those buildings to deteriorate quite rapidly. Eutrophication potential is actually appropriate that we're down here in the Gulf talking about something like this. But this is a situation which you'll find that phosphorus and nitrogen in a water supply in particular will cause the accelerated growth of certain species that can result in hypoxia or oxygen deficit within water bodies. This can cause fish die-offs and things like that. Pretty significant environmental impact, actually. Another one, ozone depletion potential. Obviously, for any of you that remember, with CFCs and things like that, we've actually been incredibly effective at reducing ozone depleting products out of our life cycle processes for almost any building material and really any material produced. They still exist in very small quantities, but this is actually an interesting category because it's one in which we've been so successful that it's now become an incredibly sensitive category where any product that even releases even the smallest amount of ozone depleting potential really stands out as quite distinct because this category is one in which we've been incredibly successful at tamping down that impact. And one that is actually of particular concern to me are things that have a very direct impact on human health. Smog formation potential is one of those. So in the course of a life cycle assessment, you can determine how much basically atmospheric pollution, low-level atmospheric pollution might be released. And smog is really the pollution that can cause direct human health impacts in the form of agitation to people that have asthma, things like that. And primary energy demand. So basically how much energy is being consumed in all of these processes. So of course in the mining of something, or you have a manufacturing process, and then even this disposal, you're going to have a certain amount of energy consumed, and in some cases, like in disposal scenarios, you might have energy recovered back out. But that's another very important category of life cycle assessment. And then lastly, and one of these impact categories, there's a little bit of a catch-all, which we kind of refer to as other categories. And these are ones that oftentimes relate to, in this case, things that are very difficult to measure, in which there's actually quite a bit of error within the science as far as life cycle assessment and life cycle impacts. So those are human health, ecotoxicity, land use transformation, and resource depletion. These are ones that, from the perspective of the type of software that we've developed, we don't actually engage because we found oftentimes the rate of error can actually exceed 100%. So it's something that we're a little leery about including because there's so much uncertainty. Imagine over time the uncertainty will decrease, but it's something to be aware of that there are other categories of impact, but there's a lot of uncertainty associated with them. So now once one has done this, you go to the next stage, which is interpretation, where basically how do you take all of this raw information? Now you know that something that has a great profile with regards to global warming potential, but is terrible with regards to smog formation. How do you interpret this? How do you actually take all of this to inform decision making? And in a lot of ways, how you inform decision making depends on the type of assessment that you're doing. So we're actually going to take you through several examples a little later in our talk, but that interpretation may come down to, say, just choosing one type of discrete product, maybe a type of insulation you'll be using throughout your building, or alternatively, your interpretation may be dependent upon something much more significant, like determining whether or not your building is actually meeting the LEED v4 requirements. So that was life cycle assessment in the span of probably about 5 minutes, which is far too fast, but it does illustrate one very important point, is that it's an enormous amount of information that ideally, if it's used to inform decision making, is available at the same time that you as a designer are making other key decisions as far as material specification. And whenever you're deciding to specify a material, you're not just thinking, boy, that looks fantastic, let's put it in the building. or you're thinking, boy, that life cycle assessment profile was great, we're done, we're selecting it. In fact, you're actually having to weigh a lot of different variables, like is this something that's even available in this particular region? Is this something that the CM knows even how to build? Is this something that, in fact, does have a good life cycle assessment profile, or is this something that the client can even afford? All of these pieces of information have to come together at the same time. And this is really one of the key skills that a designer has, is bringing all these pieces together at the same time to make a decision. The challenge that we've found as practitioners is that given the existing technology, we were stuck in this typical workflow where life cycle assessment was such a complicated process, collecting this bill of materials, getting all of these impacts together, mating them to get a proper report, was so complicated that we ended up doing a life cycle assessment multiple times at the end of the project. The information was never available at the time of decision making. And after doing this a few times, we realized, wow, first of all, it's embarrassing when we realize how bad of a job we did as far as life cycle assessment, and two, we need to find a solution. And the solution that we felt was absolutely fundamentally necessary was to have one in which you had iterative life cycle assessment, basically a life cycle assessment that was sufficiently easy to conduct that you could do it iteratively throughout the design process. So right at the beginning, you're in SD, you're able to do a life cycle assessment at that stage, and you can continue to refine one's life cycle assessment and operate the life cycle assessments on different scopes, whether it be discrete material assessments, design options, or whole building assessments, iteratively throughout the design process, so you can lead to a better eventual conclusion. So the idealized tool from our perspective is one that operated in the same modeling platform that you're using for design. At the end of the day, any type of translation that you have to do for the purpose of life cycle assessment modeling out of the platform from which you're actually making fundamental design decisions is really a step too far. You need to have something that's readily available to the designers so that as they're making these decisions, whether they're specifying a particular curtain wall or deciding if they're going to go with a steel structure or concrete and they're modeling it out, they're able to have this information right there at their fingertips. So ideal for us is that we're able to leverage the intelligence within BIM to be able to generate an extremely accurate bill of materials, combine that with a life cycle impact database, and then generate an actionable report, essentially instantaneously as you model. And of course, that report has to be one that directly informs decision making. This can't be something that just pumps out obscure figures. This has to be something that puts the information into a format that's easily decipherable by a broad audience. Something that we found incredibly frustrating is a life cycle assessment was almost the reserve of this very specialized scientific guild of LCA operators. And you had to pay an enormous amount of money to get them to talk their language to you. We want to basically put that power right back into the hands of designers. So we felt it's incredibly important that the information that any tool generate be very decipherable, very clear, and directly inform decision making. Though we also realize that there's a lot of people out there that just love data, particularly in the world of architecture. They want the nuts and bolts, they want the grit. They might be using this for very specialized research. This might have to go into peer-reviewed publications. They're going to want that real nuance. So we wanted to also create a tool that spoke to those both of those audiences, but to the same, to different levels of perhaps depth, but at the same level of accuracy. So to us, it was absolutely essential that this tool also generate information in the form of those more traditional Excel spreadsheets, where any little detailed metadata that you might want, down to the smallest little piece of how this calculation, these final life cycle impact figures were generated, is available to those users. So to talk about what all of this actually means in practice, and to walk you through the software that we generate and how that actually works, I'll turn it over to Ryan Welch.
Okay, thank you, Rod. So in the remaining, I guess, about half an hour that I have to present, I'll leave about 10 minutes for questions at the end. I'd like to walk you through about 4 case studies that demonstrate how we can apply LCA in projects not just as a post-mortem, but really through the entire phase of design, from schematic design through construction. So following these 4 case studies, I'll give a brief overview of various kind of tips and tricks that you can use during the LCA process, and then complete it with a brief discussion of how you can use LCA to achieve the LEED v4 credit for whole building LCA. This is just a screenshot of a project that our firm designed in Pound Ridge, New York. This is a house built quite recently to passive house design. And one of the things that we found through conducting LCAs on a variety of our projects is that particularly small residential projects, those with a relatively large building envelope to floor area ratio, those with relatively small quantities of steel and concrete, actually have an enormous impact that's attributable to items in Division 7, so thermal and moisture protection. Notably, insulation products are often a real killer for us when we run our LCAs. And I want to use this first example simply to illustrate that one need not begin with a complete Revit model in order to start conducting LCAs from day one. So we knew when we entered this project that we'd need to consider a variety of insulation materials to build this to passive house design. And there would be a variety of factors to consider, not the least of which would be cost, air infiltration, vapor drive, fire protection, of course, but we simply wanted to bring in LCA as another factor that we would consider along that decision matrix. So starting with an empty model, very quickly we can establish what Rod already explained is an object of study that's actually quite small in scope and breadth. In fact, it's nothing more than a representative 100 square feet of insulation. But what's really critical when you use the term functional unit is this has to provide the same function over the life of the building. So we're interested in not simply 100 square feet of 3 inches of insulation, but we're actually interested with something that can provide a particular R value over the full life of the building. So that would include material replacement, of course. And also, we recognize that different insulation products would have different R values per inch. So what we can do in our BIM model is simply to set up a comparative study looking across various insulation products and scaling their thickness to achieve the same R value. So you'll see in this view, we have a number of family types in our BIM model. We're looking at blown-in cellulose insulation, PIR, glass fiber blanket, closed cell, and open cell foam. So we really have a pretty broad study here that we can start to engage with. And when we bring that information into our BIM integrated LCA software, all of those options are at our disposal, and we can simply assign products in a quite straightforward manner. So you'll see here that the LCA database that we're pulling from, in fact, contains a variety of insulation products. So again, that same blown-in cellulose, board cellulose insulation, closed cell, and open cell polyurethane foam. So from these, we are essentially assigning materials and able very quickly to generate a report. So this report, again, is based on that 100 square foot of an R value over the full building life. And right away, we're able to generate a series of comparisons. So a couple of observations just right off the bat. You might consider that mineral wool ought to be a great product. It's natural, does not contain the foaming agents that you're typically encountering in foam insulation products. But nonetheless, it does have some pretty severe impacts associated with Portland cement, mining, and heating of coke, which is a coal byproduct. And many manufacturers actually use formaldehydes as ingredients in the manufacturing process. So it's important to note here that it's not just the materials in your actual final assembly, but it's all of those flows, as Rod suggested in that earlier slide, that go into the process that could contribute to these life cycle impacts. Another rather interesting conclusion that we were able to draw from this study was that closed cell polyurethane foam, even though we're using less of it than the open cell foam, actually had very significant impacts compared to the open cell. And that's largely derived from the fact that many, if not most, of the closed cell foams they still use HFCs as a blowing agent. And this is really something that we hope to use to be able to drive the industry. So if you speak to manufacturers and show them this data and they're not happy with this, good, because we need to get them to start producing more EPDs and integrate them into all LCA software that's available. So if you come across an insulation product manufacturer or any product manufacturer for that matter, that disagrees with the data that's being produced, that says we're doing something fundamentally different from the industry standard, have them produce an EPD, because that will really give them a lot of leverage to communicate how better they are relative to the standard of care across the industry. So in that first example we went through, a very simple material substitution, just a single, very basic functional unit. I'd like to use this next project to illustrate how we can still model at that same very abstract level of resolution, but nonetheless use LCA software to provide a higher level of detail. One common question that comes up on virtually all of our products is how we design the building envelope, how we are cladding a building. And for this particular project in Houston, Texas, we were considering a variety of options to provide shading along the south elevation. Among those, which you see here, is a terracotta rain screen. So again, very early in design, before we even have a BIM model built, we can start doing comparative studies using a simple curtain wall assembly, really nothing modeled here to speak of, but actually add that level of detail within the BIM integrated LCA software. So by setting up a series of options, we can start to compare things like aluminum composite, fiber cement, form metal panels, GFRC, and we'll see how those develop. So again, here we have a very basic abstraction of a building envelope you see in the upper right. However, when we look to the materials that are contained in the LCA entry for an aluminum composite panel, we see that they contain, down in the lower right, not only the ACM panel itself, that 76 kilograms, but also there's a fluoropolymer coating that we have to consider that might have disproportionate impacts relative to its mass. We also have to consider the not just that finished material, but also any substrates, any backup supporting structure, because again, that functional unit has to really include everything that's wrapped up in it. If we're comparing that to a different assembly that doesn't have as much structure, doesn't require as much structure, we really need to consider that in order to conduct a fair comparison. So you'll see through the BIM integrated LCA software, now we're not simply specifying a single material when we choose that cladding option. In this case, we're specifying a stone slab with an aluminum honeycomb backer, and there's a series of default options for densities. Of course, these are just out of the box. You could also override those. So if you were speaking to a particular manufacturer and were able to find that, in fact, your aluminum extrusion backup for this particular panel was actually less than your 0.4 pounds per square foot, maybe 0.25, you could actually override that and put that in here. So the idea is that this information can be applicable at day one in design before you have a BIM model made. But then as your design develops, as you have more information, more specificity in your project, you can actually update that information and essentially rerun these LCAs periodically. So this is the set of results for that study. You'll see the similar representation across those impact categories. And a couple interesting things to note here. Perhaps not surprisingly, the terracotta and the wood products come out looking pretty good. You'll see, particularly with the wood products, very low non-renewable energy impacts. Of course, more renewable energy used in that production. One thing I was a little bit surprised about when I ran the study myself was just the disproportionate impacts associated with the GFRC panel. You'll see that's in the cyan color. So those are those high peaks in acidification, global warming potential, smog, and really primary energy demand, which tracks quite closely with all three of those. And if we look a little bit deeper into that data, the data that, as Rod mentioned, is contained within the Excel spreadsheets, you'll see in this case that we're able to identify that a number of those impacts are not just associated with the finished material itself. In fact, in the case of the GFRC panel, it's really that galvanized steel support that contributes the majority of the global warming potential. So this just proves the point that you really do need to consider your functional unit carefully. It cannot just be the finished material in and of itself. It really has to encompass that whole support system. Okay, so those first two examples were not really predicated on having a BIM model complete. You really could start with a totally blank model and just build a functional unit with a representative area. The next case study that I'm going to take you through starts to look at a real project when we're a lot further along in design, and we're starting to compare different options. Options that are not simply based on a single material substitution or a single assembly substitution, but entirely different concept designs for the building. So in this particular project, this is another project of ours presently under construction in the Philadelphia Navy Yard. We're looking at different envelope options for the lower level north elevation. In the first option, the one that we ultimately went with, we have a series of storefront glazing systems interspersed with a standard brick veneer cavity wall. And in a second option, which we've built into our BIM model, it's just a fully glazed system. And then the area under that cantilever in that second option would just have a stainless steel metal panel system. So here we're finding not simply that the materials that we're using are different for that single 100 square feet, but in fact we're generating different takeoffs. And those are all leveraging the capacity of the BIM model to generate that information. And then it's simply a matter of assigning the appropriate materials and systems to those using our LCA software. So you can see in this case, our exterior brick veneer on metal stud, standard section here. And then in the second case, we have that zinc panel on metal stud where we're including stainless steel sheet material as well as tin plating. So again, those multiple co-products and bundled materials all exist in one place. And the results this time are perhaps a little more ambiguous. And this is what we commonly find on a number of the assessments that we conduct later on in design that involve multiple material substitutions. In this case, we see that there are indeed trade-offs. The fully glazed option comes out a little bit better in let's see, global warming potential and smog formation as well as primary energy demand, whereas the option that we ultimately went with comes out a little bit better in eutrophication, acidification, and ozone depletion. So this may be that sort of thing where you want to delve a little bit deeper into that data, and you also may want to consider what criteria are really most important to your project. All of these impacts can ultimately be linked to loss of biodiversity, to climate change and human health. But really, as Rod suggested, there's a lot of uncertainty in those translations. So this may be more dependent on the particular geography that you're in and the importance of different impact categories on your project. We, of course, can look a little bit deeper into that data. So that same data here visualized, broken down by CSI division, provides a little bit more of a window into what materials within each of those options are contributing the greatest impacts. And in this case, perhaps not surprisingly, that when we saw that spike in primary energy demand and global warming potential in our interspersed brick and storefront option, that's really attributable to the brick assembly. So everything in Division 4 in red under masonry constitutes that spike. And you may have thought that it was the addition of aluminum and glazing in the second option that would have contributed to the higher levels of ozone depletion, but we find it's actually a relatively small quantity of material in terms of mass, which you see right there. And that lower left side in option 2, relatively small quantity of metals. This would not include the aluminum in the storefront, but rather that metal panel under the cantilever. Despite its relatively small mass, it actually has pretty significant contributions to ozone depletion and eutrophication. So again, there's this whole interpretation phase that happens when you conduct an LCA. It's not simply about getting the results, but starting to understand where your significant contributing materials are, and perhaps making further material substitutions later on in the design. So in the last case study that I'll present, we're going to scale up to the full building. So we've seen how we can apply this at day 1 with just a simple representative area of envelope. We've seen how we can use design options later on in a project to start to investigate more complex assemblages. And then finally, when we get to a full building, of course, we can do a full building assessment. So this is a project that our firm designed in San Diego for UCSD. It's residential apartments. And you can see right off the bat there's an enormous amount of structural concrete, reinforced structural concrete in this building, as well as a number of exterior cladding that's also precast concrete. So perhaps unsurprisingly, when we run a full building LCA, we find indeed 90% of the mass is concrete. And perhaps unsurprisingly, also a majority of the impacts across most impact categories are due to the concrete. So you could think of this almost as a sensitivity analysis. We want to identify those big ticket items where if we had to make late substitutions in the game, either in CDs or perhaps even during submittal review, this would be a really useful tool. So we took this project and we did something perhaps a little counterintuitive, which is we actually copied the entire project into different design options with the idea that we would make very targeted material substitutions. So what we did was to essentially have the same baseline project, and then we take all of the structural elements that we were considering substituting fly ash or recycled materials in the mixed design, and simply replace those. So you'll see this would be the baseline, 0% fly ash. And indeed, in the lower right, you see it's using a 5 KSI structural concrete. And then we have a second option that uses an out-of-the-box concrete mix with a 25% fly ash, same 5 KSI rating. And then a third option that uses a 50% fly ash mix, same 5 KSI rating. And the results were actually quite favorable in this case. We found that a 25% substitution, that option that you see in the middle, would actually give us 10, in some cases 15% impact reduction across several impact categories. So this is obviously a substitution that we could have investigated at day one in design, just like in the insulation study. In this case, we happen to have a full building, and what's really notable here is we're seeing it not just as an isolated piece of concrete, but we understand it in the context of the full building's environmental impacts. So you're seeing that reduction in that yellow bar that's attributable to Division 3, alongside the impacts due to all of your metals, your glazing, wood and plastics, finishes, etc. So hopefully this gives you a fair sense of the breadth of LCA, how it can be really a quite accessible tool that can be applied in all phases of design, and in fact how the same studies that you apply as your design evolves can essentially be modified without having to go back to those spreadsheets and make potentially error-prone substitutions. So that concludes the case study portion. I'd like to just turn to a couple of kind of tips and tricks that we as a practice have learned through our use of LCA tools. And then I'll briefly conclude with a short discussion of the LEED v4 whole building LCA. So the image that you see before you is a suggestion that the process of LCA can become part of a really integrated firm-wide practice. Any of you that are involved in large or even medium-sized practices probably have a set of standards that you apply to many of your projects, whether you're architects or engineers. And it would obviously be unfortunate if one had to run through the same procedure again and again on every project. So we've made an effort to essentially integrate templating into the LCA tools that you see here. And one way in which we can do that is by defining all of those materials that you may use as common templates across your project, defining them in one location, the template file that you start any new BIM project within. And then as you start to develop each of those projects independently, those assignments, those material assignments, takeoff methodologies, those translations that you've made to give you your bill of materials will essentially be produced automatically for you. And then really the role of the LCA practitioner on your specific project is just about dealing with those custom assemblies. So that's tip number one. Tip number two is really in a nascent phase right now, but one kind of sweeping change that you'll see across the industry over really the next 10, even 5 years is the preponderance of EPDs, environmental product declarations. And this is really where manufacturers can start to play a role and really leverage their own best practices and communicate that directly to designers. So you'll see in this image before you, we simply ran a design option comparison comparing a generic material to one that was associated with a specific manufacturer. And we could see the impacts associated with that substitution right here. So this one actually came out quite favorably for this manufacturer. That we were able to see that there's significant reductions in the manufacturing process in virtually every impact category. So, as EPDs evolve industry-wide, I think this can really start to become a tool that can really tightly integrate with specifications as well and really drive a sweeping change. So just to touch briefly on the LEED v4 credit, which I assume most of you are probably aware of, on building life cycle impact reduction. There's a variety of ways in which you can achieve this credit, and we'll really only be touching on option 4, which is the whole building life cycle assessment. And I'll just restate it here briefly for you. For new construction, buildings or portions of buildings, conduct a life cycle assessment of the project's structure and enclosure that demonstrates a minimum of 10% reduction compared with a baseline building in at least 3 of the 6 impact categories listed below, one of which must be global warming potential, and then none can increase by more than 5%. So here, just in the lower half of the slide, demonstrated the effectively minimum threshold requirements for that. So we could pick eutrophication and depletion of non-renewable energy resources. That's that primary energy demand, that non-renewable component. And if we get a 10% reduction in those 2 as well as global warming potential with no more than a 5% increase in acidification, we would be golden. So the scope of the assessment, when we say whole building, we need to be very careful what we mean when we start to define that in terms of a functional unit. So per the US GBC guidelines for this credit, what is required is the complete building envelope, structural footings and foundations, structural wall assemblies inclusive of finishes, and floors and ceilings not including finishes, roof assemblies, and parking structures. And one can have the option of including interior non-structural components and finishes. And this is a really valuable point, because if a lot of your targeted LCA work is to improving the materials associated with your interiors and finishes, then it would certainly be worth your while to include that as part of your scope and convey that reasoning to the US GBC. What is excluded is mechanical, electrical, and plumbing, controls and fixtures, fire detection and alarms, elevators and conveyance systems, excavation and site development. As Rod mentioned, there's a lot of uncertainty associated with LCA processes, and I think one of the areas that the industry stands to achieve the great gains going forward is expanding the data that's publicly available for these categories that are presently excluded. So if your design incorporates various ideas that may have a materials cost but may save you a whole lot in mechanical systems, unfortunately at this point that's not something that you can justifiably include within the LCA, but I would certainly take that up with your US GBC representatives, and perhaps there are ways to work through this issue. So just to reiterate the last case study that I showed you, where we saw that impact reduction due to the fly ash substitution, indeed that option with 25% would meet the threshold. That is, we have a 15% reduction in acidification, 11% in global warming, and 13% in smog formation. So, problem solved. Now, the process of reporting, and really the LCA process in general, is really an iterative, comparative process. It's not intended that you wait until a building is complete, run an LCA, make a couple substitutions to try and game the system. You really do need to show that you've used this to generate actionable data to inform your material substitutions, and that's something that's really important to convey through your narrative to the USGBC. And there are a couple of ways that you can do this with LCA software. One can simply run a report, make those substitutions, and then compare results from a second report. One can also use the design options, as I suggested, as a way of generating a report that combines two scenarios in one place. A couple other tips and tricks just regarding troubleshooting. This is something that we find through experience on doing LCAs. There's an enormous amount of information that goes into these, even both on the back end in terms of providing those LCA data points, but also as a user of BIM integrated LCA software. And one thing that we find quite commonly is that our BIM models certainly don't include everything that's in the building. And there are ways in which we need to translate between that level of abstraction that you saw in that second example, that second case study. And there's also things that we may model that are extrinsic to the building. You may model sidewalks as floors, and unless you figure out ways of partitioning those and separating those out of your scope of assessment, you may find that your volume of materials is really off. So it's really important to read through the results of your report. If something doesn't make sense, look to the metadata, look to the masses that are calculated, and if you find that there's 15,000 tons of brick in that building assembly, when you have a pretty good intuition that it should be lower than that, it's probably because you've had a lot of brick sidewalks that have been mistakenly included and assigned. So just be mindful of that. Another thing to note is that not all BIM categories are included. So things like generic models that don't really have a category assigned to them really should be avoided so that you can properly identify things as walls, floors, ceilings, etc. And then, as I mentioned, work sets, which, if you're not familiar, are a way of partitioning model elements into separate bins and generally intended for work sharing and collaboration. Those can be a really helpful means of avoiding that plague of the sidewalks being included in your assessment. Another key item to consider is that if you're working with linked models, let's say you have a detailed structural model that probably has the best representation of all of your structural floors, foundations, etc., it's probably a good idea to define those materials in that model. But then if you have them reproduced in your architectural model, you really want to make sure to exclude them and set them as what in LCA practice we would term a dummy material. Another potential area of concern is in the service lives. So as I mentioned before, a functional unit is not just what you need in the building at day one, but it's what you need to essentially preserve the same function of the building through its valuable life. So if you assign a material that has a replacement rate of 1 year and your building life is 60 years, you're going to get a 60-fold duplication of that material's impacts. So be mindful of the service lives that you select, and while there are certainly a lot of pragmatic defaults that are built into the system, if you have a particular project, say a commercial interior, where you know your interior partitions are going to be replaced every 10 years, you're going to be repainting perhaps every year, it's really important to include that in your study. And if you're combining that with potential substitutions of less impactful finished materials, then it'll actually come out quite favorably for you. And then finally, takeoff methods. What's built in a BIM model is not necessarily an accurate representation of reality. one rarely builds cold form metal framing, for instance. The takeoff methods that are built into the interface of the LCA software allow you to kind of navigate that level of abstraction that you'd find in BIM in order to get the real quantities of material that you need to conduct LCA, namely kilograms. And with that, that concludes our talk, and right on time. I think we have about 10 minutes left for questions. I know that was a dense amount of material, so I hope to answer any questions you may have. Yes?
I actually have few questions. I did miss the beginning, so just let me know, and I'll come up afterwards if it's repetitive. But one, is there a way to integrate cost of each of the elements into this, so you could factor the upfront costs? So you could factor that in?
Upfront costs, or perhaps even lifecycle costs would be a natural extension to that. At this point, with the software that we've demonstrated here, no, not yet. That's certainly something that we're considering for the future. I think there's probably a lot of data out there that would be very regionally specific, because that would factor in labor costs. So we didn't attempt to solve that problem just yet. So unfortunately, I think you still have to go perhaps the traditional cost estimation route at this point. One can certainly take advantage of BIM software nonetheless to generate schedules to feed to a cost estimator. But I think what you'll find is that the level of resolution and material detail that you need to conduct an LCA is significantly higher than what you would need to conduct cost modeling. So that those complex wall assemblies for which we need to account for the brick, the sheathing, all those materials. I think a cost estimator would typically look at that assembly as a whole and cost that. So I think that would be one thing that we need to navigate, is that the different degrees of resolution.
Also, is there a way to aggregate all of the various impacts into one overall? How does this?
That's a great question, and certainly there are categorization schemes out there that do attempt to aggregate again the acidification and global warming down into impacts that are more intuitively understandable, like loss of biodiversity indexes, human health, global warming potentials are already in effect in an intuitive endpoint. With aggregation comes a higher level of uncertainty in terms of how those various impact categories come together and what the weighting systems are. There are already a number of weighting systems in place just to generate global warming potential as an expression of a carbon equivalence, because there are other chemicals that may be emitted to the air during the manufacturing process, methane just being one of them, that are essentially converted into a common fungible unit, namely kilograms of carbon or carbon dioxide. So we felt that this was a kind of fair middle ground between that. The short answer is a qualified no at this point. However, as I mentioned, there are schemes out there. Recipe is a common one that we're certainly looking to in the future. I think that the real concern, though, is if we can justifiably include it based on the uncertainty that we find in our sensitivity analysis.
And finally, is there any way to learn through this what the actual reason is that it's manufactured in this way and that's why it's having this impact? Because I find I would learn more and then be able to apply that next time, and not always have to go back if I understood the.
Yeah, that's a great question, and there is a little bit more metadata that we didn't really want to make this a complete demonstration of the tool itself, like a demo, but there are copious amounts of data contained in the output reports that provide an indication of what data sources have been used for those inputs. There's generally a lot of LCI, lifecycle inventory information, concerning the scope of the manufacturing, as well as end-of-life assumptions. So in terms of the percentage recycled versus landfilled versus incinerated. However, I think your question gets to really the heart of LCA, which is understanding at a much finer level what points in the manufacturing process may be the most significant contributors. And for that, I would certainly direct that question to LCA practitioners. Certainly, there are folks here, PE International, Athena Sustainable Materials Institute, who do that professionally on a daily basis and can provide that information, those services. To a certain extent, those data points are bundled up for the sake of the databases that we've presented here.
Thank you.
My pleasure. Yeah. Any other questions?
Yeah, I have a quick question.
Sure.
I'm wondering, just thinking about costs and how, what inspires people to sometimes want to take on sustainability measures and that sort of not being part of the equation here. I'm just sort of wondering from your perspective, what's driving your clients to want to pursue LCA assessments without out of the picture?
Yeah, well, I can answer that in a couple of different ways. There's certainly a lot of folks within academia that have a pure academic interest in applying this. The LCA, as it applies to whole buildings, is a fairly new field. There's not really a lot of baselines that, like we have for energy modeling at this point, to establish a benchmark against which we can compare. So I think there's a certain just academic interest in the subject. I think there's also a recognition that our buildings are becoming more energy efficient, and with that comes a kind of change in the proportions of the relative impacts that are associated with operations, namely energy use during the building's life, and the impacts associated with construction. And remember that the impacts that are associated with the construction are recognized on day one, like the day that a building is built, whereas the operational energy impacts are only realized over the life of the building. So I think there's that initial impact that you really do need to consider. So that's the kind of academic side of it. I think there's also certainly a market drive for it, not the least of which is USGBC and LEED taking on as a credit. And the wording of the credit, if you're kind of reading between the lines, leaves a lot open to interpretation. And I think the intent of that credit is really to get people to start thinking about this, because it's widely recognized that this is a new field. It's not necessarily well understood by architects at this point, to the extent that they understand energy modeling, and I think we recognize that it's going to really need to be considered as buildings become more energy efficient, and as we have obviously a huge amount of global capital investment in new construction over the next 30 years. So, yes. Sorry, can you speak into the microphone?
Is this available as a plugin or as a cloud service, or?
Yes. Oh, okay. So yeah, we kind of danced around the issue. So the particular tool that we demonstrate here, Tally, is a plugin to Revit. So you can download it off the Autodesk Exchange or via our website, choosetally.com. And I think we probably have a couple of cards around. Just see us afterwards to get that information.
So is it a cost? Because there was an earlier thing, was a lighting analysis. I know the lighting analysis is free, but it goes, the payback's through cloud credits. Is this the same thing?
No, it's actually a completely third-party plugin. So it's not part of Autodesk cloud system.
Oh.
It's a separate database.
And just one other question. You mentioned the EPDs for manufacturers.
Yes.
Are they available as data, or would you have to actually type all the information in? I mean, where you can get an EPD from a manufacturer?
So the EPDs are a published public document.
Right.
That contains an LCA, a peer-reviewed LCA by a third-party program operator. the data contained in that LCA would then be fed into here. There are certain adjustments that we would make to account for consistent functional units. So if we have an EPD from one cladding manufacturer that doesn't include steel support and another one that does, we would need to essentially make them a little bit more fungible.
But that's, I mean, some of it's integral in the software, but to the extent that it's not integral in the software, if we get an EPD from a manufacturer, I mean,
Yes.
manufacturers, I guess I'm just curious, do they supply this in an electronic format?
Yeah, like
Or
a PDF.
typically,
Yeah. Yeah,
PDF,
yeah.
but you still have to type it in.
No. So when, in order for us to put an EPD into our software, we do have to do a little bit of processing to ensure that it has a consistent functional unit with the other things that you might substitute it for. The best thing would be to contact us, data@shoestally.com, to basically get that process started. But there's, hopefully Rod managed to convey just the utter complexity that goes into producing these data points. So we just want to make sure that the scope of those EPDs are consistent with the data that we're putting in, and if they're not, we need to make some corrections to that. So that's why there is that a bit of a step. It's not just about entering, like copying in that information.
Yeah, thanks. Many of your displays with regards to the impact categories are defined, almost predefined by the end user, the information, but the end user also, and the EPDs often refer to additional information, additional technical or environmental information.
Sorry.
Is it possible that, is there room for additional relevant environmental information to be included in this data set that may not be part of the impact categories? Other attributes that aren't tied directly to an impact category? No, that's in the actual communication, because this is communicating information, relative to the effect of, with regards to the takeoffs and the build materials and everything else. But part of the communication of environmental impact information is something that's outside the categories of ozone depletion and global warming potential. Does the tool have the ability to include that in the final output, like report or summary or whatever else?
So if I've understood your question correctly, there's the short answer is probably not. It's a defined set of impacts according to the Tracy schemes. However, let us know. I mean, we're a small development team. We're pretty nimble. So if there's certain information you feel is missing, I mean, one thing, I don't know if this is specifically what you had in mind, but human health impacts are things that we have not included in this for reasons that Roderick already explained. But nonetheless, it is still certainly relevant to material considerations, of course, as we all know. And we're actually looking at different ways in which we can start to integrate a little bit more fluidly with some of those other ways of measuring material health and environmental impact. So I think as this reaches a little bit more maturity, I think you'll start to see some more of that information put in. But if you have specific wishes for things that you'd like to see or resources, public resources that you'd like available, definitely let us know.
I don't recall if you said anything, but when it comes to some of these numbers too, it deals with end-of-life treatments and what's happening at the end of life with regards to waste management and recycling and
Yes.
mass flows, energy flows with regards to recovery for energy.
Yep.
Is that inherent to these numbers? The
Absolutely.
end-of-life
Absolutely. So
scenarios?
you may have seen in some of these slides, actually the slide right here might be a little too grayed out to see, but you'll see on certain output reports, there are actually negative impacts or credits, and those are associated with what's effectively an avoided burden. So if we're able to demonstrate that there are materials that are recycled or recovered for incineration that effectively avoid the burden of primary material extraction and refinement, those are counted as credits according to the accounting scheme. And then secondly, incineration would go to offset some of the primary energy demand.
So you're assigning that into those quote-unquote credits and avoided impacts into the system boundary of the building versus it happening or applying to the next cycle, the next system.
Sorry, can you repeat that?
So your system, as it's defined here, is applying those credits, such as avoided impacts or offsets, recycle issues of raw material, into this system versus the next system.
Yes.
Which is really where the benefit happens.
That's correct. Yeah. The LCA accounting mechanism that we're using is the avoided burden. So we assume all the full impacts at the outset, and then account for the credits at the end of life. And you're clearly speaking from a very informed position on this. Otherwise, you wouldn't have asked the question. And I would encourage you to talk to Nick Santero, who's part of our development team at PE, who's responsible, essentially chief for generation of the LCA data set that's used in the tool. So he may be able to answer that with a little bit more detail.
It all has to do with the base LCA system or tool that you're using, and what the end user, like USGBC, says, okay, you can apply those avoided impacts and benefits to this system or not, and that's where it's sort of the cutoff all happens of the decision. Anyway, thank you.
Yeah. All right. Any other questions?